Hello, and welcome to Controllers Tech. A while ago, I created a video that demonstrated how to interface an SD card with an STM32 microcontroller using the SPI protocol. While the example in that video worked perfectly fine, it involved a somewhat complex configuration process for the libraries, which made it difficult for many viewers to follow. Since then, ST has significantly changed the structure of their codebase, which makes that older method even more confusing, especially for beginners who are just starting with STM32 development. Today, I'm introducing an updated library that simplifies the entire setup. This new library is not only easier to configure, but it also comes with more features and better performance. One of the major additions is the support for DMA in SPI communication, which allows for much more efficient data transfers. It also enables multi-block read and write operations, which greatly improves the speed at which data is accessed or written to the card. This updated library supports a wide range of SD card types. Whether you're using a standard capacity SDSC, high capacity SDHC, or extended capacity SDXC card, this library should be able to handle it without any issues. As we proceed through this video, I'll walk you through how to use this new library step by step. I'll also show you some of the key functions available, and towards the end, we'll run some benchmarks to evaluate the read and write speeds using both DMA and non-DMA modes. To follow along, you can download the library files using the link provided in the description of this video. Once downloaded, you'll find all the required files neatly placed inside the SRC and INC folders. I'll demonstrate exactly how to organize them within the project structure as we go forward. Let's begin by launching STM32 Cube IDE and creating a new project. For this tutorial, I'll be using the STM32 F103C8 microcontroller, which is the chip found on the popular blue pill board. Start by giving your project a name of your choice, and then click on Finish to create the project. Once the project is set up, the first step is to configure the system clock. Enable the high-speed external HSE crystal, since the blue pill board comes with an 8 MHz crystal oscillator. We'll configure the system to run at its maximum frequency of 72 MHz. Also, be sure to enable Serial Wire Debug, SWD, which is required for debugging STM32 F1 controllers. Next, go to the Connectivity tab and enable SPI1 in full duplex master mode. While we will configure the detailed SPI parameters shortly, let's first review the default pin assignments provided by CubeMX. By default, SPI1 uses PA5 for SCK, PA6 for MISO, and PA7 for MOSI. However, in my setup, I have connected the SD card module to PB3, PB4, and PB5 for the SPI signals, and PB6 for the chip select or CS pin. We'll reassign the SPI pins accordingly. To do this, hold down the Control key and drag the assigned SPI pins to their new locations on PB3, PB4, and PB5. These pin selections are based purely on convenience, as they make it easier for me to connect the module to the board physically. Now I need to configure the PB6 pin as a GPIO output, which will be used as the CS line. Rename this pin to CS for better readability later in the code. Next, let's configure the SPI peripheral parameters. We'll start by adjusting the prescaler to reduce the SPI clock frequency to around 2 megabits per second. This speed is generally safe for most SD cards, though you're welcome to experiment with higher clock rates. Up to 10 megabits per second should work fine in many cases. The rest of the SPI settings will remain at their default values, with 8-bit data size, MSB first, clock polarity set to low, and the clock phase configured to trigger on the first clock edge. If you plan to use DMA for data transfers, now is the time to enable it. Make sure you enable DMA for both the transmit and receive directions. Set the DMA mode to normal and configure the data width for both memory and peripheral to 8 bits. To see logs and output data on a serial console, we also need to enable UART. In this setup, I've connected the transmit pin, PA9, to an STM32 USB to serial converter, which allows communication with the computer. We'll enable UART1 in asynchronous mode. The default settings are fine here, with the baud rate set to 115,200 bits per second. Now return to the GPIO configuration and adjust the CS pin we configured earlier. Set its initial output state to high, as this is the idle state for the CS line. Also, change its output speed to high, because the pin will need to toggle quickly during communication. The next step is to enable the FATFS middleware, which we'll use to work with files on the SD card. Inside the FATFS configuration, ensure that the makeFS function for formatting and setLabel for assigning volume labels are both enabled. Additionally, enable support for long file names and make sure to use a dynamic working buffer located on the heap. This will allow us to work with file names up to 255 characters long, instead of being limited to just 8 characters for the name and 3 for the extension. Leave the rest of the FATFS settings at their defaults. That means the sector size remains 512 bytes, and we'll be using only a single volume. One crucial step before generating code is to disable the automatic initialization of FATFS. To do this, go to the Project Manager tab and open the Advanced Settings. There, disable the code generation for FATFS initialization. The reason we do this is because our custom FATFS driver implementation will handle all the necessary linking internally, and we don't want CubeMX to interfere with it. Now that everything is set up, generate the code. Once the project is created, open main.c and notice that the FATFS initialization code is not present, which is exactly what we want. Before we move forward, let's quickly build the project to ensure there are no errors. If the build completes successfully, we can now move on to importing the library files. Copy the .c files from the downloaded library into the src folder of the project, and copy the header files into the inc folder. If you've downloaded the complete project from the link, the files will already be arranged this way, so just match what you see here. Let's take a quick look at the contents of these files. The SD_SPI.c file handles the low-level SPI communication with the SD card. At the top of the file, you can choose whether or not to use DMA by setting a flag. Then you define the SPI instance you're using, in this case, SPI1, and also define the CS pin and its port. You don't need to change anything beyond that point. This file includes functions for sending and receiving data, initializing the SD card, and reading or writing blocks. Next, we have the S_diskio.c file, which serves as the bridge between our SD card functions and the FATFS middleware. It contains the required driver functions that connect the low-level operations with the FATFS stack. This means we don't need to manually configure any of that in other files. The third file, SD_functions.c, includes higher-level functions that make working with the SD card simpler. You'll find functions for mounting and unmounting the card, reading and writing files, listing directory contents, and more. All logging in this project is done through printf, so we'll also define a custom function that redirects printf output to the UART. Make sure you point it to the correct UART instance in case you're using something different from mine. Let's now take a look at how to actually use this library in our code. Begin by including the SD_functions.h header file at the top of your main.c. This file gives you access to all the core functions required to work with the SD card. Inside the main function, we'll begin by mounting the SD card using the SD_mount. Once mounted, we'll call the SD_list to display all the files and directories currently stored on the card. Finally, we'll unmount the card using the SD_mount. I've already copied a few files and folders onto the SD card beforehand, so you should be able to see those printed in the serial console when we run the code. Let's now build and flash this project to the board. Once it's flashed successfully, open up your serial monitor. and make sure it's configured to 115,200 baud, which matches the UART settings we used earlier. Now insert the SD card into the module and press the reset button on your board. In some cases, especially when using DMA for SPI, the SD card may show a not ready error on the first attempt. This usually happens because the card hasn't completed its power-up sequence. If you see that error, just press the reset button again, and it should work on the next try. Once the SD card is successfully detected, you'll see a message in the console showing the card type. In this example, the card type is SDHC, and it has a total storage size of 16 gigabytes. Right after that, you'll see a list of all the files and folders located at the root level of the SD card. In my case, I got a file 1.txt and two folders named F1 and F2. Inside the F1 folder, there are additional subfolders named F1F1 and F1F2, and there are more files placed inside those as well. This confirms that our file listing function is working correctly and the FATFS integration is successful. Now that we verified that the SD card is detected and the files are listed properly, let's try reading a specific file. For this demonstration, I'll be reading a file named file5.txt. This file is located inside the F1/F1F2 directory structure. To read this file, we first define a buffer that can hold more than 30 bytes of data, since the file size is exactly 30 bytes. We also declare a variable to store the number of bytes actually read. Inside the main, we'll again mount the SD card, then use the ST_read file to read the contents of file5.txt into our buffer, and finally, print that buffer to the serial console. After that, we'll unmount the card. When you run this code, you'll see that the contents of the file are printed correctly on the console. This confirms that our file read operation is working as expected. Let's now try reading another file, file1.txt, which is placed directly in the root folder of the SD card. This file is larger. It contains 71 bytes of data. So we'll increase the size of our buffer to 80 bytes to safely store the entire file content. The procedure for reading the file remains exactly the same. Mount the card, read the file, print the content, and unmount the card. You'll now see the new file contents printed on the console, and the number of bytes read will match the file size. So both the reading operations for files inside folders and for files at the root are working perfectly fine using this library. Let's now move on to another important operation, writing data to a new file on the SD card. Just like with our previous operations, we'll start by mounting the SD card using the SD_mount. Once the card is mounted, we'll move forward to creating a new file named file6.txt. This file will be placed in the root directory of the SD card. The function SD_write file requires two arguments: the name of the file to be created and the actual data that you want to write to the file. In our case, we're writing a simple text string, which is approximately 36 bytes long. After writing is complete, we'll call the ST_read file to verify the result by reading the file back. We'll print the contents of this buffer to the console using printf. Once that's done, we'll also call the SD_list, again to display the updated directory structure. Let's now build the project and flash it to the STM32 board. After flashing, we'll open the serial monitor to check the output from the microcontroller. As you can see in the console output, the driver reports that it successfully wrote 36 bytes to file6.txt. Immediately after that, we read the file back, and the data printed on the console matches exactly what we originally wrote. This confirms that both the write and the read operations are functioning correctly. We also printed the directory listing, and right there in the root folder, you can now see the presence of file6.txt, along with the earlier entries, file1.txt, and the folders F1 and F2. So we can confidently say that file creation and writing operations are working perfectly with this updated library. Next, let's take a look at a slightly more advanced operation, reading data from a CSV file. This is very useful in cases where data logging has been performed in tabular format, or when external systems generate CSV logs that need to be parsed by the microcontroller. I already have a file named file4.csv stored inside a folder called F1, and within that, another subfolder named F1F2. This file contains 16 rows of data, with 2 columns in each row, which is the standard format for CSV files. To read this file, we will use a special function from the library called STM32 CSV. Before we call the function, we need to prepare a data structure that will store the contents of each row. This structure, already defined in the library, typically contains 2 fields, Field 1 and Field 2, both stored as character arrays. We'll then define an array of this structure, large enough to store multiple records. In this case, we'll allow for up to 20 records, even though the file only contains 16. Alongside this, we'll declare an integer variable named record_count, which will store the number of rows that were successfully read by the function. Once everything is set up, we'll call the function ST_read CSV. We'll pass in the full file path f1/f1f2/file4.csv, along with the array to store the data, the maximum number of records to read, and the record_count variable. Internally, the function will open the file, read each line, split the line using the comma as a separator, and store the resulting 2 values into Field 1 and Field 2. As part of the process, the function will also automatically print each row to the console, so you can see the data as it's being read. To take this a step further, we'll also debug the project to inspect how the data is stored in memory. Let's place a breakpoint at the while loop. When the program hits the breakpoint, we can open the Variables tab in the debugger and examine each entry in the array. You'll see that the record_count shows 16, which matches the number of rows in the file. Let's check the console now. The function has successfully read the data from the CSV file, and you can see the output right here. Each row begins with a serial number. For example, the first row starts with 01, followed by 2 values that represent the actual data in that row. You'll notice that there are exactly 16 rows, numbered from 0 to 15, and each row shows 2 columns of data as expected. This confirms that the CSV file was read correctly and the data was parsed and printed in the proper format. Inside the structure, Field 1 contains the data from the first column of each row, and Field 2 contains the second. All of this is stored as character arrays, making it very easy to process or display later. This confirms that the CSV reading function works flawlessly, and the structure-based approach allows you to manipulate the data in a very clean and organized way. Now that we've seen how to create, read, and parse files, let's try some additional file operations, like appending new data to an existing file. This is useful when you want to continue logging data without overwriting what's already there. In this example, we'll append 22 more bytes to file 6.txt, which we created earlier. We'll use the function sd_append, passing the file name and the new data we want to add. After performing the append operation, we'll again use sd_read file to read the entire content of file 6.txt and then print it to the console. This allows us to confirm that the new data was added correctly. Let's also test the file deletion feature. In this case, we'll remove file 1.txt from the root folder. We'll do this using the function sd_delete, which only requires the file name as a parameter. Once the file is deleted, we'll again call sd_list to refresh the list of files on the SD card. When you look at the output, you'll see that the total file size has now increased from 36 bytes to 58 bytes, and both the original content and the newly appended text appear one after another, just as expected. Also note that we no longer see file 1.txt in the list. This confirms that the delete operation worked as intended. With that, we've now successfully tested all major file operations: creating, reading, writing, appending, deleting, and even reading structured CSV data. Let's now test the read and write speed of this library using the built-in benchmarking feature. There's a file named ST_benchmark.c that helps in performing this test. Inside the file, you can choose whether to enable or disable the usage of DMA by modifying a simple flag. You can also define the test file size if needed. By default, the benchmark creates and works with a 500 kilobytes file to test how fast the SD card can read and write data. We'll begin by testing the speed without using DMA. First, make sure to set the DMA flag to 0 in both the ST_SPI.c and ST_benchmark.c files, which ensures that the polling method will be used for all data transfers. Then, include the benchmark header file in your main.c and call the benchmark function inside the main function. It's important not to call the mount and unmount functions manually here, because the benchmark function already handles that internally. Let's now build and flash the project to the board. Once flashed, wait for the test to run completely. You'll see the results printed on the console. In my case, the write speed is reported to be around 194 kilobytes per second, while the read speed is approximately 67 kilobytes per second. To confirm the consistency, let's reset the microcontroller and run the test once again. This time again, we get the same speeds. I repeated this a third time, and the results were identical. So, we can say with confidence that, in polling mode, the SD card delivers around 194 kilobytes per second for writing and about 67 kilobytes per second for reading. Now let's perform the same benchmark test, but this time with DMA enabled. To do this, go back to the ST_SPI.c and ST_benchmark.c files and set the DMA flag to 1. This allows the library to use DMA for transferring data over SPI. Build the project again and flash it to the board. On my setup, I encountered a disk initialization error on the first boot. This can sometimes happen when using DMA, especially if the SD card was not ready or fully inserted. Simply reset the microcontroller and the test should start running. Now that the benchmark is started, we'll again wait for it to complete. Once finished, check the console for the new speed results. Interestingly, the write speed remains nearly the same, around 194 kilobytes per second, but the read speed increases drastically, going up to nearly 200 kilobytes per second. This is expected, as DMA makes data transfers much more efficient, especially for continuous read operations. To further validate the library's compatibility, I tested it with a different SD card, a 1 GB SDSC type microSD card. After inserting the card and running the benchmark, the console correctly identifies the card type as SDSC with a total size of 1 GB. However, the write speed on this card turned out to be much lower compared to the SDHC card. The read speed was still acceptable, but SDSC cards generally don't perform as well in terms of writing, especially with larger files or higher transfer rates. Still, the important point here is that the library successfully detects and supports SDSC cards, in addition to SDHC and SDXC cards we've already seen. Now that we've verified the core functionality, you can explore many more features that this library offers. For example, you could delete files, rename them, create new directories, and append data to existing files. Each of these operations is implemented through simple function calls in the code. I encourage you to try them out yourself after downloading and setting up the project. This concludes the demonstration for the SPI-based SD card interface using the updated library. But this is not the end of SD card tutorials. In the upcoming videos, I'll cover how to use the SDIO interface, which provides even faster data transfers and more efficient communication compared to SPI. After that, we'll also explore the STMMC interface, which is commonly used in STM32 devices that offer high-speed memory card support. You can download the complete source code for this project from the link provided in the video description. It contains all the configuration files, source and header files, and a fully working STM32 Cube IDE project, so you can try it out on your own hardware. If you run into any issues or have questions, feel free to leave a comment below. I try my best to reply to as many as I can. Thank you for watching this video. Keep learning, keep experimenting, and, as always, have a great day ahead.